Here we've made measurements of vapor-liquid equilibrium, or in this case we generate data with noise on a computer, and then we fit that data using nonlinear regression for the two-parameter molecules equation, and we calculate these two parameters, A12 and A21, and then use nonlinear least squares, where the difference between the experimental measurement of the gas phase mole fraction and our calculated gas phase mole fraction for component A is minimized. We calculate the gas phase mole fraction from the starting liquid phase mole fraction, saturation pressure from an Antoine equation, and pressure of the system, and the activity coefficients gamma A, and the log of the activity coefficient is related to these two parameters and the liquid phase mole fractions. So we've generated a spreadsheet that carries out these calculations and also calculates the confidence limits for these parameters. So let's look at that spreadsheet. So here's the spreadsheet where we have properties of the two components, A and B, their Antoine equation, calculate their molar densities, pressure of the system, 760 millimeters of mercury, and then here are our measurements. So we carry out their measurements by mixing together different ratios, different volumes of components A and B to total 100 milliliters. And then we measure the mole fraction of A that's in the vapor phase. And we're assuming that very small amount of the vapor, which is present in a total reflux as a condensate, this amount is small compared to liquid, so the liquid composition we calculate from our starting materials is pretty close to the liquid composition at equilibrium. We then measure these mole fractions of vapor phase and the temperature, and then we calculate from these measurements. First we have XA and XB. Antoine equations give us the saturation pressures. We calculate the pressure, which was held at 760 in experiments, and because of noise, it doesn't always add up to 760 when we calculate it from the saturation pressures and the mole fractions and the activity coefficients. So the experimental measurements for A, gas phase mole fraction, and the calculated value, which are calculated from the activity coefficients from the two-parameter Margulis equation, and here are the activity coefficients we calculate. We compare this difference, and that's what we then minimize the sum of the squares. So sum of the squares, we name this cell SS. We're going to minimize that by varying the value of the two parameters. These are the values we're going to end up fitting using solver. These are the values that were used to generate the data. So we generated data, added noise into it. That's where we got the gas phase mole fraction measurements. And so what we end up with are these parameters repeated here, just two significant figures, and their confidence limits. And so the way we minimize, we use just mole fraction of A to minimize. We could actually use both the mole fractions of A and the mole fractions of B that we calculate from the modified Raoult's law and the activity coefficients and saturation pressures. That's what this cell is. If we do that in solver, we get almost the exact same answer. These two other columns are comparing the experimental measurement for A and B to the average, the mean for A and B, and we use that to calculate the R-squared value. The spreadsheet has detailed explanations of what we're doing. It also shows a plot of YA versus XA, and you can see the fit is the orange line from the modified Raoult's law, and the squares are the data points. Confidence intervals are calculated over here. The way we do that, these are our minimized values. What we do is set a value different. So, for example, we go over to here and type in to this cell 0.62. And then we use solver, vary the value of just A21. So we're going to minimize the sum of the squares, but just using A21, we fixed A12. We solver, we get this value 0.0128. That's a value show here. Repeat that for other values. When we do that, we get this plot, the blue curve, and then this orange line we calculate from the equation which is given here, and I won't explain where this comes from because this limit time we have, but The intersections between the orange and the blue, these are the two confidence limits. And we do the same thing now for A21. So we fix A21 at different values and we get the sum of the squares using solver. So now we can go back to the correct values for minimized are listed here. And we get, remember, we got those by using solver. So we go to data and solver, and we're going to vary A21x and A12x. And I've named the cells, and that's why I can write these terms for the cells that we're going to vary. And then we get the values that we have also copied up here. Well, you'll notice the values are not exactly the same as the data we started with because of the noise, but they're actually pretty close for A12, and they're certainly within the confidence limits.